Moore Creek Dam in Australia. So this dam, these are the details which are given. Now, between 1898 and 1911, the reservoir was filled with 85,000 cubic meter of sediments. In 1924, the dam was out of service because the reservoir was fully silted 25 years after its construction. So you can see here that because we did not fully consider the sediment transport in the design, clear. So what happened is that 25 years after its construction, it was fully silted. This is an old photograph of the dam, that is the Moore Creek Dam in Australia. You can see here initially when it was constructed, and now today this is the new photograph. You can see here that because of the silting, it has reached its life span. So this is because that these failures, these are caused by these sediment transport processes. So the rivers on which we build these dams, they carry these sediments. And if these sediments, they are not incorporated into the design of these hydraulic structures, so you can see here that these structures which were constructed no longer serve the intended purposes. This is another example. We have this dam. It was fully silted, clear. This was built for the railway water supply. You can see here it was fully silted. Similarly, we have the Cunningham Creek Dam. It was a railway dam fully silted in less than 20 years. So you can see here that these are the examples of the failures that was caused by the sediment transport processes. And as I said before, that because we are constructing these hydraulic structures, dams on natural rivers, so definitely the rivers, they carry these sediments. So the design or the life of these hydraulic structure will depend on the amount of sediment that is carried by these rivers. So the thing is, what we can do, if we can analyze, for example, we construct Torbella Dam. So Torbella Dam is constructed on the Indus River, and the Indus River has several tributaries which are joining the Indus River, and those are coming from the northern areas. And they carry the sediments. So eventually the life of the Torbella Dam will depend on the amount, the nature of the sediments that are coming in the water to the reservoir. So what we can do, for example, you have heard about the Deamir Basha Dam. So we have the Basha Dam, and the Basha Dam is constructed upstream of the Torbella Dam. Clear? This Basha Dam that is constructed upstream, let me see that we have the Torbella Dam. Clear? This is the Torbella Dam. And upstream of this on the Indus River comes this Basha Dam, which is under construction. So you see here that in the initial years of operation, this Basha Dam will retain the sediments. because they will retain the water and then allow the water, so the sediments will get a chance to settle in the reservoir. So it will reduce the inflow of sediments to the Tarbela Dam. And it is estimated that the life of the Tarbela Dam will increase by 30 years because of the reduced sediments inflow to the dam. The life will increase by 30 years. Now, this is not the way that how you can increase the life of the dam, that if you want to increase the life of a dam, build another dam upstream. If you want to increase the life of a dam, build another dam upstream. No, I'm not trying to explain this concept. The idea here is that because we construct a dam, so you try to reduce the inflow of sediments to the Tarbela Dam. Remember, Basha Dam, it is designed for full flushing of the sediments. It means that it will allow the sediments to pass without settling in its reservoir. It is designed like that because with the passage of time, we improve our knowledge, our design procedures. So you can see here that reduce the inflow to the Tarbela Dam. The life of Tarbela Dam will increase by 30 years. Other ways to do it is that, let's say we do not have this dam. So you already know that you have studied hydrology, that we have this catchment or watershed, and the water which is coming in the streams, so that is contributed in the river, and on the river we built a dam. So this weathering and erosion which takes place, we can try to reduce that. For example, in this picture you see more trees. So you see the trees, they are beneficial because the roots of these trees, they will keep the soil intact and it will prevent the erosion due to the natural processes. For example, we have rainfall, we have snow, glaciers that we have. In such type of cases, you see that if there is snow, it will try to erode the material, surface material. Or we have glaciers, so as the glacier move, the material are carried along. So that's why we can do watershed management. These are the ways we can reduce the sediment in the rivers and ultimately the sediment to the reservoir and to increase the life of the reservoirs. But however, in Tarbela Dam, it happens that we are constructing another dam upstream. So because it will retain the sediments during initial operation, that will reduce the sediment inflow to the Tarbela Dam, and it is estimated its life will increase by 30 years. So you can see here these means that we apply to reduce the inflow to the reservoir, and it can continue for more time. This depends on our understanding of these transport processes of the sediments. Because initially we did not consider them in the design of the hydraulic structure, so that's why you see that the failure of the structures that happen in the past. So you can see that study of this sediment transport, this is now very important. So we will have introduction to sediment transport in open channels. Because this is hydraulics and mostly we study with flow of water in channels, so that's why we will mainly focus on sediment transport in open channels, natural streams, rivers. So we see that commonly in the mountainous regions, as we saw that this weathering and erosion, this is the source area. Commonly we observe rainfall here happens, we have slopes, materials, if they are loose, they will be eroded by the rainfall or the glaciers that melt, and then those sediments they will carry along in the water for distances, depend on the size of the sediments. If the size is very small, then it is carried to longer distances. If the size of the sediment is more, they will travel for shorter distances before settle down. So you studied geology, we have weathering and erosion in mountain source area. Once the materials are eroded, then they are transported downstream by the river systems. And ultimate deposition of sediment in the coastal marine environment. You can see here that whenever the river joins the ocean or the sea, so maybe you observe there that these sediments, they are deposited there. So in this case, we already know that we have mountains in the northern areas of Pakistan where you have the rainfall that takes place, the precipitation or the snow, and then that water, it travels in the streams, tributaries originating from here. They joins the Indus River, and then on the Indus River we have, for example, just to understand, we have constructed the Tarbela Dam, and then after the Tarbela Dam the water passes and it continues in the Indus River, and you already know that that Indus River is ultimately going to the ocean. So the sediments which are heavier, they may cover some distance and deposit here. That's why at the foot of the mountain you will see the loose material. Those decrease in size, they will continue to flow with the water. And that will depend, how much distance they will cover will depend on the transport power of this medium water in the rivers. Some sediments come here, for example, in the Tarbela Dam, we store the water. So some sediments will get deposited here. This is what is happening in all the reservoirs built on the natural streams and rivers. And the remaining water will continue to flow if, for example, some very fine sediments, they will continue to flow until the final point of deposition here. So these are natural processes and these are occurring over a period of time. This is not that these are new processes. These are happening. But because we face problems here, you can see that we design a hydraulic structure and now we cannot operate it for the intended purpose. So we come across that what is the problem? We see that it is completely silted because we did not fully understand the sediment transport processes. So that's why we need to study this topic in order to address those problems. So we start step by step from the very basics and then we move towards complex topics. So sediment is a naturally occurring material that is broken down by processes of weathering and erosion and is subsequently transported by the action of wind, water, or ice, or by the force of gravity acting on the particles. So once the material is eroded, then it can be carried, transported by, you see, wind, water, and ice. The glaciers you already studied might be that the glaciers, they also move. So these are the carriers for these sediments, the medium. So in this course, our main focus will be water as the medium for the transport of sediments. We will mainly focus on this thing. But you can see that how wind is transporting the sediments. You see in the deserts, wind is blown and the sand or other sediments, they are transported from one place to another place. Similarly, the glaciers, they move from one point to another point, carry the sediments along that are trapped. So you can see the vastness of the course of the topic. So we will study mainly with the sediment transport in water. And because the water in natural streams and rivers, they flow due to force of gravity, so that we consider in the mechanics that we study of the sediments, the gravity force. For example, sand and silt can be carried in suspension in river water and on reaching the seabed deposited by sedimentation. So sedimentation is the settling of the material. Because sand and silt smaller in size, they are carried in suspension. We will study the mode of transport in the water. The alluvium or sediment refers to the loose, non-cohesive material such as sand and silt transported by suspended in or deposited by water. So whenever we say alluvium deposits, it means that they're related to water. Because here we study, it can be wind, it can be ice, it can be water. So whenever you see the term alluvium, alluvial deposits, alluvium, clear? So it means that that is transported by, suspended in, or deposited by the water. That is why even there can be a full topic, alluvial hydraulics. Now, sediments are most often transported by water. So these are fluvial processes. These are called fluvial processes. But sediments also can be transported by wind, which are known as Eolian processes, and by glaciers. But remember, here our main focus will be on fluvial processes. The word sediment refers commonly to fine materials that settles to the bottom. Technically, however, the term sediment transport includes the transport of both fine and large materials such as clay, silt, gravel, and boulders. Now you study sedimentation, you studied environmental engineering. So in that case, we have sedimentation tank. And as the water comes here, the water is allowed to remain in the tank, and the idea is that the particles, they settle down. This is sedimentation. And then the remaining water, that is withdrawn. And then if still we have particles, so you already know we add coagulants to the water so that flocks are formed. That's why we have coagulation and flocculation. And still the remaining can settle down. And if we have microorganisms, then we have disinfection, chlorination, that we normally do in the water treatment plants. So that is actually this settling, that is sediment. Clear? Sediment refer commonly to fine materials that settles to the bottom. But in sediment transport, in addition to this concept, because as I say that in the river, let's say this is the water surface, so there will be some heavy sediments also. So they will also move due to the action of water. So that's why the term sediment transport also include transport of both fine and large materials, because you see that clays, silt, gravel, bigger size boulders are bigger size than gravel. So this can be, for example, boulders. So they also move because of the action of water. So that's why in sediment transport, It includes the transport of both fine and large materials. Sediment transport is the general term used for the transport of material, clear, in rivers and streams. So our main focus will be that on water, clear. We are not going to focus on these, how sediments are transported by wind or by glaciers. Our main focus will be related to fluvial processes, fluvial hydrodynamics, clear. Sediment transport is essentially two-phase flow problem in which the fluid phase is air or water and the solid phase is sediment particle. So now so far we studied open channel hydraulics. We only consider the flow of water and we study the hydraulics of that. Now we bring in the sediment particles. So you can see here that this sediment transport is more complex now, because now essentially it is a two-phase problem. One way is the first fluid phase, that is water or air, and the second phase, the solid phase, that is the sediment particle. So now you can see that sediment transport is now more complex. The processes of erosion, transport, and deposition of sediment, collectively termed as sedimentation, are natural processes and have been occurring throughout the geologic time. So as I said before, that this erosion of the materials, and then they are transported and then they are deposited at the point of deposition depending on the transport power of the medium. So these are happening throughout the geologic time. These are not new processes. So these are happening since the beginning. Now we are interested to study them because the hydraulic structures that we design, they are failed. So we see what is the problem. So in order to solve the problem, we need to study the mechanics of the problem, and that's why we reach here sediment transport. Now, sediment transport mechanics, sediment load or sediment discharge is the total amount of sediment transported by a stream or river past a given point, expressed in terms of weight per unit time. Just like you measure the water and the volumetric rate is cubic meter per second. This is how you measure the water, it is in discharge. Clear? Q, volumetric flow rate, or the mass flow rate, that is rho Q for compressible fluids, or the weight flow rate, that is gamma into Q. So for compressible fluids, then we can measure in kilogram per second. We are not much concerned with compressible fluids, so that's why we commonly use this volumetric flow rate. Now you have sediments and you want to measure sediments, so in terms of weight per unit time. For example, if I go back, just in an example, that for example you have this Yellow River. So on the average, annual sediment load is 1.6 billion tons. So this is 1.6 billion tons per year. So this is what it says, that how we measure that this river is transporting how much sediments. So this is the total amount of sediment transported by stream or river past a given point, expressed in terms of weight per unit time. Now, based on the predominant mode of transport, sediment load can be classified into bed load and suspended load. This is how the sediments, they are transported, mode of transport. So we can divide the total sediment load into these broad fractions, the bed load and the suspended load. Because we already discussed here that it can be clay, it can be silt, gravel and boulders. So because you see the size is different, small size to large size, that's why you see how the boulders will be carried in suspension. They will definitely move along the bed like I explained here. And smaller particles, they can be carried in suspension. So the total load can be divided into bed load and suspended load. So how we define them? Bed load is the fraction of sediment load that moves by saltation. I will explain, show you in picture what we mean by saltation. Saltation is the jumping. For example, you have this material here, sediment, which is placed on the bed, and then the water is coming here and it pushes the water, because you see we have turbulent flow. So velocity will have components in the XYZ direction. So it will try to push here, push. So this material, it will go up, it will come here, and because it is heavy, again it will try to then settle here. Then from here again it will be pushed by the water and it will go up, and again because of the gravity it will settle here. So this is how it is transported from this point to this point, and then from this point to this point, and so on. And it will depend on the transport power of the water flowing in that river or stream. So this is actually saltation. This is saltation. And rolling along the stream bed. Rolling means that it can roll also. Instead of going up, if we have very heavy, it will just roll. For example, it will just roll. So then it will continue to be like this, then coming here, then coming here, rolling along here. Because it is very heavy, cannot go up. So just by rolling, it will move. And it will continue the motion till the resistive forces are greater than the force of the transporting of water. So bed load is a fraction of sediment load that moves by saltation and rolling along the stream bed, primarily by the action of the bottom shear stresses caused by the vertical velocity gradients. So now we are actually studying the mechanics of sediment transport. We say that if we have a particle, let's say this is the sediment, so you see on one side the force is acting to move because it is in water, then it has the gravity component which try to stabilize it on place. And because it is in contact with the bed of the channel, so there will be some shear force that will try to resist the motion. So if the gravity component and the shear stresses, if they are more than the transport power of the water, this will remain in place, it will not be moved. But if here the force, this is stronger than the gravity and the shear force, it will move in this direction. This is exactly similar to what you studied friction in your engineering mechanics course. This is exactly similar. So we study the mechanics now of the sediment transport. So bed load is this, which moves along the bed by different mechanism, saltation or rolling. I will show you the pictures. The second one is the suspended load. It is fraction of the sediment load that moves in suspension by the action of turbulence. Because we have turbulence, that's why the particles that are smaller in size, which cannot settle due to this, their less weight, they will continue to move in water in suspension. So now we have the sediment load, and that can be divided into these two classes. So that's why if we are able to discuss the sediment transport in detail, Then we will be interested that how much sediments are carried in suspension in Indus River. How much sediments are carried as bed load in the Indus River? And what is the total sediment transport? We have different formulas for this if we discuss this sediment transport in detail. Now, particles transported as bed load are coarser than the particles transported as suspended load. So you already know this. If a particle is light, clear, finer particle, it will be carried in suspension. If a particle is heavy, then it will be as a bed load. Some particles may move as bed load at one point and as a suspended load at another point. So this will be the middle particle size. That's why now all the geotechnical engineering that you study about the soils, their sizes, now we are going to study as part of mechanics in sediment transport. Maybe in the next lecture we will see the properties of the sediments. So that's why the middle size particles, they may move as a bed load at one point and may become suspended load at another point. This will depend on the conditions. Based on whether the particle sizes are represented in the stream bed, sediment load can be classified into bed material load and fine material load. This is another way of looking into the problem. So what is the bed material load? The bed material load is the fraction of sediment load whose particle sizes are significantly represented in the stream bed. So it means that you have the bed of the channel of the stream, and because we say that because of waters erosion takes place, so let's say the material is eroded from here, and now this material, it moves in the water as sediments. This material removed and it moves in the water as sediment. So bed material load is the fraction of the sediment load whose particle sizes are significantly represented in the stream bed. You will see that these sizes will be significantly present in the stream bed. So we say bed material load. And we have fine material load, commonly referred to as wash load, is the fraction of sediment load whose particle sizes are not significantly represented in the stream bed. For example, some particles are coming in suspension in water. So from where these originated? Maybe these are originated somewhere in the mountains and they move, continue to flow in the streams. And here we measure the sediment load. So because these sizes are not represented in bed here, so that's why these are known as fine material load. Now, bed material load is the coarser fraction of the sediment load which may have originated in the channel bed. I already explained. And that may be subject to deposition under certain conditions. Wash load is finer fraction of sediment load that has not originated in stream bed and that is not likely to deposit because it is coming from longer distances in the mountain, continue to here, and even it will reach the ocean ultimately. Also, I show you the pictures. So wash load is largely unaffected by the hydraulics of the flow. For example, I told you, you have a large sediment material, particle here. So you want to study the mechanics. So we say, okay, force of water is acting on this and it has the gravity component and then the shear force acting here because of contact. So we study, will this particle move or not because of the flowing of water. This we will study in the next lecture in detail. We can predict that the particle which is here will move for the given conditions or not. This is known as incipient motion, and we can calculate this. This we will study in the next lecture, but the thing here to understand here is that we can study the mechanics of these particles here. But let's say you have this particle or some of the particles which are very, very small. How you will study the mechanics of this? So that's why it is stated that wash load is largely unaffected by the hydraulics of the flow. This is the classification that we just studied. So we have the total sediment load, that can be the wash load, suspended, bed material load, or bed load. Clear? So what we can say here, broadly, these is suspended load or bed load. Based on predominant mode of transport, we already said suspended load or bed load. Based on whether particle sizes are represented in the channel bed, so we have wash load or bed material load. We already studied all these. So this is the classification. That's why when we estimate, for example, here the value which is given in this example here, let's say you are asked to calculate what is the sediment transported by the Indus River. Actually, I don't have the data on the Pakistan River, so that's why we mention here rivers from other countries. If we have data available, I will give you here the Kabul River data, the Indus River data. So here it is mentioned that 1.6 billion tons per year sediments are transported by the Yellow River in China. So this is actually the total load here. You see, it will be the suspended, it will be the bed load. Clear? Depends on the conditions. The conditions are not fixed. Clear? So in general, we say that the material will be transported in suspension. So this is how we classified them. As I said, when we study in detail, this sediment transport is a course. So we will say that how much bed load is transported by that river. We have different formulas developed by different researchers. We can study, just like, for example, in open channel, you have the Manning formula, you have the Chesy formulas. We have similar situation here. You are interested that how much sediments are carried as suspended load in the river. Again, we have different formulas for this. We can estimate. And we will do sampling. That we will study in the next lecture, based on which we do the analysis and we develop the formulas to estimate. And the third can be what is the total sediment load. So that can be combination of the two. That can be combination of the two. So if we are going to study this in detail, then we can study all these equations related to this in detail. Now, flowing water transports sediments as bed load that we just discussed. Particles can roll, slide, or bounce along the bottom. Or particles that can be carried as suspended load. Particles that can be carried as suspended load. So these are particles carried above the bottom by fluid turbulence and grain collisions. This is what you can see here, that if we have bed load, in here we have bed load, so the particles can move as rolling, it can roll, it can slide, or it can be impact and creep, another particle coming and pushing here, or it can be by bouncing, jumping. This is known as saltation. Goes up and then falls down, then goes up and then falls down. This is known as saltation. And the suspended load It can be by collisions, because you have sediment, they can collide with each other and push along, and due to the turbulence. So this is how the water transports the sediments, the bed load and the suspended load. This is another example. You can see here, if the particles are large enough, we can study the mechanics. You have the weight component of the particle, you have the shear, fluid shear, the bottom shear, the uplift that is created so that it can jump and again it falls down. So for that we can develop equations that will include these: what is the mean velocity of flow, the depth of water, the fluid properties, and so on. So when we study mechanics of the sediment transport, then we have to consider such forces acting on the sediments. You can see here we have the river bed. So due to the traction, the particles can move, that I already explained here. So we can have saltation by jumping and move along, can be by suspension, you can see here, and also very fine particles, they can also move in solution. So in solution, then it becomes very difficult that you apply the hydraulics. That's why it was written here that largely unaffected by the hydraulics of the flow. We just do as much as possible. Clear? So you can see here, by traction, the particles can move. By this jumping here, which we say saltation, or by suspension, or as in solution. This is another figure. You can see here the bed load, which it can move here, and we have the dissolved and suspended load, which will move in suspension in the water. So we have suspended load within the water column, supported by turbulence, typically silt and smaller particles. We have the bed load for the sediment, typically silt or larger size gravel boulders. By traction means rolling and sliding along the bed, saltation by bouncing. So this is how these we define the suspended load, the bed load, and then the total sediment load. So let us see small videos about the sediment transport. You can observe here the sediments are moved, and also you can see the bed of the channel that is changing because the sediments are removed or deposited. So the stow side, lee side, upstream, downstream. Again, you can see here how the sediments are transported. See the bed and also some of the material, they are transported in suspension. So this is how the materials that are transported. To continue with the discussion, you already observed in the video that the materials, they were removed from the bed, and then the material moves along the bed, and then it is deposited also. So that's why you can see that it can result into different bed forms for the rivers and streams, because somewhere the material is removed, somewhere the material is deposited. So that's why it can result into different bed forms in the channels, in the streams, in the rivers. So in most practical situations, sediments behave as non-cohesive materials. For example, sand and gravel, and the fluid flow can distort the bed into various shapes. These are the reasons that sediments behave as non-cohesive materials, and the fluid flow can distort the bed of the channel of the river stream into various shapes. This interaction process is complex. Free surface flow over erodible sand beds generates a variety of different bed forms. So because of the flow of water on erodible sand beds, so that will result into different bed forms and bed configurations. The type of the bed form and dimensions of a bed form depends on the properties of flow, fluid, and bed material. We will study now different bed forms that can result. So why they result into different? Because they will depend on the properties of the flow, the fluid, and the bed material. Now, bed forms are typically classified into a low flow regime for subcritical flow and an upper flow regime for supercritical flow with a transition zone close to critical flow. This is how these are classified in sediment transport. The bed forms associated with these flow regimes are as follows. So because here that we studied, they can result into different bed forms, and different bed forms, the type and dimension will depend on the properties of the flow, the fluid, and the bed material. That's why we do not have just one type, maybe different types, depends on these factors. So we have the lower flow regime, we have the ripples, we have the dunes. In the transition zone, these are the types of bed forms. I will show you the pictures. In the transition zone, we have bed configurations range from dunes to anti-dunes. In the upper flow regime, we can have plain bed with sediment movement, anti-dunes, breaking anti-dunes, standing waves, chutes, and pools. So these are the different types of bed forms that can occur depending on the factors that we discuss. So we have flat bed. You can see here, this is flat bed. You can observe here no sediment motion. We can have this type of bed formation. These are known as ripples. You see the small size. And in that case, these typically occur when the Froude number is very much less than 1. So these are ripples, you see. Then when Froude number is still less than 1, these grow in size, and these are known as dunes. Now the important thing here is that these ripples which form, they will also appear to move in the direction of flow. Dunes, the movement of the bed, you see, you already saw this in the video. I will show you again. This bed form motion will occur along the direction of the flow under these conditions. You see, we have standing waves where Froude number is equal to 1. You see here, looks like the wave is standing. Then we have antidunes. You can see the flow is supercritical. Froude number is greater than 1. So in case of dunes, you see the movement of the bed, that will be in the direction of flow. But antidunes, they appear that the bed moves in opposite direction to the flow. I will show you. But this will not happen for greater distances. How can the material here moves upstream for kilometers? No. This will be just for very short distance, but it can happen depending on the flow conditions. I will show you. So because they move in opposite direction to the flow, that's why these are known as antidunes. And we have this pool formation. Then you can see chute, steep slope, again pool formation. So these are the different bed forms that we can observe in sediment transport studies. Now these are ripples. This is an example. When you see the bed of the channel, stream, river, these are known as ripples. These are an example of dunes. You see the size is then big as compared to the ripples. So this is how we classify them into dunes and ripples. Clear? This is how visually we can differentiate between them. So let us watch some video for this to understand. This is ripples. Try to show in this video. So you can see the bed configuration, it changes because of the movement of these sediments. So this is kind of an example of ripples. These are also ripples. You can see, observe the bed. You see, and the motion is in the direction of flow. You can see they are advancing in the direction of flow. That's why we have different bed forms. You can see here, observe closely the bed. Now you can see here, the speed is increased for understanding purposes. So this is how you see that they move in the direction of the flow, ripples. Now this is dune migration. You will see the size will be big. Dune migration. You can see here, observe the bed of the channel, it changes. That's why we have different bed forms subject to the different conditions. Now you can see here the size is big. So dune migration, and also in the direction of flow. So this is how you see that we observe these different types of bed forms. Clear? Now ripples and dunes, they move in the downstream direction, means along the direction of flow. This is what you see here. You see here the bed form motion for dunes I show you in the video. Similarly, the small size, so the ripples. You see the bed form motion that is in the direction of flow, downstream. In the anti-dunes opposite, I will explain why. So ripples and dunes move in the downstream direction. And this is the mechanism we try to explain that how it moves. So you can see here the dune migration. So you can see here that the material that is removed from here and that get deposited here, this is how this surface appears to move in the forward direction. Similarly, from here, the material will be removed and it will try to deposit here. So this will appear to advance as you saw in the video. So ripples and dunes, they move in the downstream direction. I show you the videos. Anti-dunes and step pools are observed with the supercritical flows, and they migrate in the upstream flow direction. They migrate in the upstream flow direction. For example, you can see here that we have anti-dune migration. So this is the flow direction. And when erosion takes place, this material will be depositing here. And what happens that this face appears to move in this direction because eventually it will become here. So this appears that anti-dune migrate in the upstream direction. Of course, this will be for short distance. It cannot be that the material from here can travel way back to the point of origin. It is not possible. So this will be for short, very short distance. And if the fluid flow is, because you see it is supercritical flow, if the velocity becomes strong enough, it can flush the same anti-dunes in the downstream direction by the water. So this bed form movement migration appears upstream for anti-dunes. Let me show you some video to understand this. You can see here in the lab, the movement is opposite to the flow. You can see here, the movement is opposite to the flow. This is anti-dunes. You can see another video here for anti-dunes. The water is flowing in this direction. You will see that anti-dunes migrate and then the strong water currents come and they are flushed downstream. You can watch again, you see that it appears to move in opposite direction. Look here, it appears to move opposite to the water. These are anti-dunes. but then they breaks here due to the flow of water again coming here. You can watch another video. The water is flowing down. You see here anti-dunes move up and then they are flushed down. You can see here they move up and then the water currents are strong, so they are flushed down. So this is how these anti-dunes, they appear to migrate in the upstream direction for short distance, depending on the flow conditions. And as I said, if the flow currents are strong enough, because we have supercritical flow, again it will be flushed in the downstream direction. So these are the different bed forms which can occur in sediment transport, and we study their characteristics. So we will continue with this discussion in the next class.